major fraction have done. How many of you have done cryptography? Only very few. How many of you have done network security course in elective? Great. Okay. So the way I have devised this talk is, I'll be kind of giving a premise of the network. What is a network? What are the different protocols? And then why you need network security, and what are the different mechanism and strategies in the design. So this talk will be kind of unconventional, because I will not be touching on the cryptographic things. It's kind of a dry subject. Probably you might have known those who have taken cryptography. So the intention of this talk is, at the end of this session, you will understand why you need to apply this technique, and what is the fundamental premise. You will be understanding why I should do, why I should be doing it, why it works in a way it works like that. But we will not go into deeper roots of it, which means we are not going to study the cryptographic mechanisms that provide that services. We'll be kind of touching that in terms of black boxes. Okay, so as Dr. Balaji mentioned, I'm handling the network infrastructure of IIT Tirupati. Since this is a new institute, we are kind of creating the new network infrastructure, and then we are working from the design stage itself. Okay, and my PhD area is in the networks, so I chose to do that thing as a part of my personal interest. Okay, so the flow of the talk will be like, it will not have any top down approach or bottom up approach that you have followed in your networks course. Probably you might be, since many of you have raised your hands on networks, you know what is the protocol stack. Why is a protocol stack in networks? So typically some courses in networks, they will take a top down approach. They'll teach you from the application layer, go all the way back to physical layer. Some people teach in a bottom up approach, where they start in a physical layer and go to the application layer. But the way this talk is structured is, I will not be following any top down or bottom up. I'll be kind of using a mix and match of these things, just to give you some continuity in the flow of why security is needed and things like that. So the way we are going to understand this network security is from a network administrator's perspective. For example, we are going to take a toy example of a campus network. In a campus network, how a network is designed, why a network is designed in that manner, and then we'll see what are the attack surfaces that can appear on these network structure. Okay, so that's the kind of approach you are going to take. So you are going to see the network concepts and strategies from the lens of a network administrator. So I'll be kind of switching back and forth between the whiteboard and network slides. So feel free to ask questions at any point in time. Okay, right. So first thing is, why do we use network mostly? What is the major application of the network? For communication. Okay, and communication among the people within the campus or across the globe. Across the globe. And what is the most common communication substrate that is connecting all the computers around the globe? Sorry, random. LAN and WAN, these are the technologies that contribute part of your network. But what is the most predominant service or the network that connects everybody in this globe? Yeah, that's a keyword, right? Okay. Why is this named as internet? It's a simple question. Why is this called as internet? What is an internet, by the way? It is a network, fine. But what is internet? Internet is, you can think of this term as a acronym. Okay. The full expansion of this is internetworking. Or internetworks, because internet is composed of network of networks. Okay, so basically you can think of that as, you have a network 1 which is connected to network 2, which is connected to network 3, and so on and so forth, because there is no single entity on the earth that manages the whole network. For example, if you take this college, the SSN college, they have their own IT team. They maintain the campus network. This is one part of your network. For example, you have an internet connection in your home. Okay, so what you get, what you procure in order to get an internet connection? Your ISP, internet service provider, will give you an internet line. Okay, it could be some earlier days it was on a telephone line. Now it is a broadband. Some fiber will come. From there, he will take a copper cable, Ethernet, and then that will come to your router. From that router, you will connect all your wired devices and wireless devices, right? So everything that happens within your home is a network by itself. That is, let's say you are in your home, you have a Wi-Fi router. Let's say this access both as access point and router, and from the ISP provider. So this network is maintained by ISP, right? And then you will get a cable that is connected to that access point or the router, and then you have all your devices um, connected to this over the wired connection or over wireless connection, right? So this itself is a network on its own. Okay, this is your home network, right? So this is a network by itself because you have all your devices that can talk to each other, even if that internet is down. Okay, you can talk to each other locally because you have your own network of devices. And what is this? This is a network maintained by the ISP. Probably if you have taken an internet from the Airtel or from Reliance, they have their own network. Why they have a network? Because ISP is not serving only you. It may be serving multiple homes, multiple residences, and multiple companies, right? So likewise, they will be serving multiple clients. Each of these you can consider as networks, and then they will all connect all these uh, networks via routers. So that has its own network. And then probably this ISP provider may be a small scale provider. You might not be maintaining a large part of routers. He will be in turn taking lease from a big player, right? Okay, maybe this could be some local service provider. He might have taken some bandwidth lease from a major provider like Airtel or Reliance and things like that. And finally, they will be connected to some other access networks. And then you have a hierarchy of networks. And this is how multiple parties, business organizations maintain network. And your internet is composed of the entire thing. Okay. So this entire network of networks, you call it as internet. So hence you have the name of internet, which is basically inter-networking, network of networks. Okay, so that's the kind of name that we use. How to okay. So now to understand, to quickly recap the basic functionalities or services protocols provided in the networks, let me quickly recap the OSI protocol stack. So can anyone help me up? What is the bottommost layer? Let's call it as link layer. So there are 7 layers in the stack, but predominantly there are 5 layers. We are going to see only the 5 layers. Okay, there are multiple versions here. I'm just using 5 layers. Okay, so I'm not going to the session or presentation layer. Okay, So we are going to understand the attack surfaces and kind of security mechanisms in each of these layers in a very high level perspective. And first things first, what do you mean by a protocol? Perfect. So a protocol is a set of rules. And why do you need a protocol? Why do you need a protocol? Yeah, you can take the real world analogy. For example, let's take a person coming from a country A who speaks a language A, another person who comes from country B who speaks language B. Okay, it doesn't suffice to make two people meet to each other because they cannot talk to each other. Because person A speaks language A and person B speaks language B, it doesn't suffice. It is not enough for two people to just come and speak. A medium is not just a sufficient condition. You need to have a common rule so that whatever each person speaks should be conveyed to the other end, and you have to communicate. So to establish communication between any computing devices, you need to have a set of rules, and these set of rules are not single monolithic framework, because network has a lot of components. And for your to put the things in perspective, internet is the single most fascinating invention ever made by human being, which is the most complex network, which is now difficult to understand. Okay, and which is the most artificial man-made invention, which is very popular since its inception. Okay, so the reason is there are a lot of protocols that works in a distributed manner, and that still keeps our internet in a more stable condition. Okay, um, and this is not just for the networks. The entire computer science subject relies on three important principles. Okay, those are: one is protocols, which is set of rules, because set of rules is not only applicable for networks. You will see any other domain in computer, you will have a set of rules there. Your language, programming language, follows a set of rules, right? So many things follow some architecture and rules. So protocols is necessary. And the other principles in CS discipline, which is very important, is abstraction. And okay, so if you want to put entire computer science subjects into some common theme, if you want to understand, these are the things that you will repeatedly get back to here in terms of different cosmetic layers. Okay, what is an abstraction? Yeah. So abstraction is you are hiding the details. You just need to know what it does. That is sufficient enough, but you don't need to know how it works the way. Can you give some real world analogy of abstraction? Yeah. Yeah. So that is one kind of abstraction. Um, uh, to put one more example, let's say if you want to drive a car, right? So you need to know what happens when you steer the wheel. When you turn left, the car should turn left. When you apply brake, the car should stop. When you press the gas pedal, the car should accelerate. So this is a kind of abstraction. But you don't need to be a car engineer to understand how it works. All you need to know is an abstraction, right? It's a very simple thing. Many things that you see in the world is kind of abstraction. You need to know the interface, how it works, but you don't need to know how it is actually implemented. This abstraction is also there in the programming language, especially in C. What is that? Okay. Oops. Oops encapsulates data and functions. Even C has its own abstraction because you modularize the whole program in terms of functions. You just need to know what are the parameters that you need to pass and what it does and what is the return type. You don't need to know how it is implemented, right? So that is a level of abstraction. So abstraction is a key principle used across your computer science in the field of computer science. And what is decomposition or hierarchy? If you have a big problem to solve, you break the problem down into multiple sub problems so that you focus on solving that problems, and then you kind of arrange these sub problems vertically or horizontally. And for example, you see this whole network as a problem. Okay, what you have done is you have decomposed horizontally, sorry, vertically, into multiple stacks where each layer does some functionality, and each layer is an abstraction of its own. And you have decomposed the whole problem into a set of five mainstream problems, and you have given some sort of solutions in terms of protocols and methods, right? That's how you can understand a protocol stack. Okay. Next page, next page. Okay, right. Okay. Okay, so there is nothing much to discuss in the physical layer, because physical layer is mostly how you transport the information in the medium, in the way the medium can understand. And you know that in a physical layer, basically you use different types of technologies, medium technologies. One is wired, the other one is wireless. In wired, what are the predominant types of communications, or what are the predominant wired medium used in networks? Ethernet, which is a copper cable. The other one is, sorry, I didn't get it. RJ32. I think it is a standard for a copper cable. What is the other medium? What is the limitation of an Ethernet cable? Ethernet cable has a limitation of a maximum distance it can cover. To today's technology, there are different versions of Cat6 cable. Right now, Cat6a is the current standard, which can support up to 10 gigabits of bandwidth, and it has a maximum distance. Any device that you want to connect, it can be connected in an Ethernet cable, which can cover a maximum range of 100 meters. Okay, so that's why in a kind of campus network, you will see that Ethernet cables are kind of used in the labs and other settings, but you cannot connect an Ethernet cable between two computers that are kilometers apart. Okay, because Ethernet cable has its own limitations. Okay, what is the other way of if you want to extend this two computers beyond 100 meters, what you are going to do? Fiber is one way. The other way is you connect with multiple switches, and then you connect with chain of multi switches and extend your coverage. There are multiple ways to do it. So what we'll be focusing here is, end of the day, you will not see only the network security aspects. You will also see how to design a campus network. If I want to establish a big IT organization or an enterprise like campus or an IT company, which is going to connect several hundreds of computers to to an internet, to an ISP, or to connect to the internet, what are the things that I'm going to do in that, and what is the objectives that I need to take care of in terms of design aspects? Because in a security, you need to first focus starting from the scratch, which is the design. If your design is flawed, then a lot of attack surfaces will be opening up. So you can think of a design of a network as a part of security mechanism. Okay, so I will not be focusing much on the physical layer. Let's move directly to the layer 2. Okay, so layer 2 is called as a data link layer, or you call it as link layer in short. What is the purpose of a link layer? Let's say, for example, I have a computer, which is the host 1, which is connected over physically to host 2. Okay, this is called as link, right? Right. So what is a link layer? Why do you need a protocol in a link layer? I have a physical wire that is connected from this side to the other side. Everything is fine. To give a big picture, a link layer focuses on the link level aspects. Your typical network doesn't look like this. Okay, in a typical network, for example, in a lab, there are multiple computers, n numbers of computers. How How are these computers connected? Let's say I have host 1, host 2, host n, let's say 100 computers. Okay, let's say for example, let's say I have 20 computers. Okay, how are these computers typically connected? I want to connect these computers to the internet. In your home computer, you have a router. All of these are connected to the routers, right? So here in a campus network, you connect to a device. Usually, when you put a box and cross, that is called as a switch. Okay, to be very precise, it's a layer 2 switch. Okay, so you will have multiple ports in the switch, and you will be connecting in a star topology. This is the last part of your campus network, which will be connecting your end devices in a wired network. Okay, have you ever thought like why the star topology was used? I can also connect this in a different manner, right? So how many ports are required in the switch? So each one is a port. So if I have 20 computers, I will be consuming 20 ports in my switch. Okay, if I want to reduce my ports, what I can do? Can I use a bus topology? So the other strategy or other hypothetical design is I have an L2 switch. I want to reduce the number of ports because I have a very big network. I don't want to reduce the number of switches. What I can do is I can do a bus topology, like you see in your computer organization, right? One Neumann architecture, right? You have a system bus. In a similar way, can I do something like this? Right? This is also a good design, right? I have reduced the number of ports. Then I can use all other ports to connect some other lab computers. But this is not a typical network design that is followed in today's world. What is an engineering approach behind it? I'm just asking, wondering. This is where the network administrator's perspective of network is required. Okay, this kind of concept you might have missed in your network course. But what do you think is beneficial when I go with a star topology? Sorry, in what way? Good. So, so this is more reliable. Reliability is high. Why? Because when there is a cut in the cable, your entire network of computers will be disconnected. That is one important aspect. This is also a security in terms of design, right? So this is an attack surface. I can even cut the cable and I can completely segmentize or isolate a network of computers. Right? But in this star topology, you need to cut all the wires um, along the way, and that is one thing. But that's not a real requirement here because this is in a kind of a well maintained or protected environment. You won't let anybody to get in to do all this stuff. So there is another important benefit from this topology in terms of performance. Can you guess what is the performance? To understand that, so this will increase um, the performance in terms of throughput. Okay, in computer networks, we'll be using throughput and bandwidth as an interchangeable word. Okay, which essentially represents what? What do you mean by a throughput? What is a unit for throughput? What's the basic unit of throughput? Throughput is rate. Rate is bits per second. Okay, how many bits I can push per second. Okay, so whenever you buy a router, what is the most important metric that you see? I want more throughput, more bandwidth, right? you want to buy a 1 gig router or you want to buy a 10 gig router, you focus on in 1 second, 1 unit of time, how much data I need to push. More the data you push, more the bandwidth. So this star topology increases the throughput performance of each of the computers. Okay, how is that? You need to understand a little bit about the throughput performance. If I have a medium, this medium is giving me a throughput of, let's say, 1 bits per second, and there is one computer that is connected to another computer which is here, and ideally, theoretically saying, practically you will get less bandwidth, but what is the maximum thing that you can push theoretically is you can push a traffic of 1 bits per second to the host, right? If you are sharing, let's call this as channel, physical channel, because it could be wired or wireless. And if there is another computer that is coming here, which I am connecting it through this, like a bus topology, there is one physical wire and then 3 computers are connected. Now the bandwidth is shared, right? So more computers are connected to the physical wire. It is something like you have a road. Okay, one vehicle is there and it uses one lane. Okay, it uses one full lane, something like that. Or to put in different analogy, let's say you have a pipe, right? Then the pipe has a diameter. Diameter of the pipe is the bandwidth. More the diameter, more the bandwidth, more fluid can go into the pipe. So when you are connecting one tap, all the bandwidth can be consumed by the tap. When you're connecting 2 taps, the bandwidth is shared. When you connect more taps, more bandwidth will be shared. It's a simple analogy, right? So now you go back to the previous one. In a bus topology, you have one wire, and let's say the current standard of our physical technology in Ethernet is Cat6a. Cat6a is the current standard, which gives a maximum bandwidth of 10 gigabits per second. Okay, if I connect 20 computers, 20 computers will share this 10 gig per second. Okay, so I'll be using how much? It is 10 gigabits divided by 20, right? 0.5 gig everybody will get. But here I'm using the same physical cable between the host to the switch. So each host will get to a maximum of 10 gig bandwidth, right? So that's the key idea. So reliability is one aspect that is fine because, but anyway, the access is going to sit near your building. Nobody is going to cut that, but performance is the most important aspect here. Okay, and this is how the star topology is provided. And what is a link layer? Now the question is, uh, link layer aspects come here in a very has a very less importance here, but link layer aspects become very important when you are doing a wireless connection. Okay, what is a wireless connection? You replace this whole setup. In a wireless connection, what do you do? Your switch, you replace it with an, what will you do in a wireless or a similar setting like this? What do you do? Right, you have Wi-Fi access point, which is a layer 2 device, and then you have host 1, which is a laptop. You have another host 2, which is a laptop, and then you have, which is a laptop. All are not talking to a wire, it is connected wirelessly, and this access point has a coverage range. Right, what's the difference between these two setups? Are these two setups are ideally equal? In terms of topology, they are equal. All are connected to the access points. In terms, you are replacing your wired with a wireless connection. Are there any engineering challenge in this wireless communication? Sorry. Right. Eventually, the difference here is obviously when you see this is a wire, right? So when you have a wire here, that is the medium that connects the two devices. but here wireless is a broadcast medium. Okay, so this entire shared medium. So shared medium, when it comes to security, anything that is shared is dangerous, because even an attacker can come in and use the shared medium, eavesdrop others' transmissions very easily, and then they can attack your communications in many levels. They can eavesdrop. They can also kind of behave like a proxy access point, because in a wireless access, in a link layer, access point is also one end device and your host is another end device. An attacker computer can also act as an access point. So when you come to some region, you can also connect to an access point which is genuine, or you can connect to an attacker's access point which you don't know, because the broadcast medium is a shared medium. Okay, and the other question is, um, the other important point here is, let's say this access point gives you a bandwidth of one, uh, let's say 10 megabits per second for our understanding. Okay, when all 10, 20 computers are there, what will be the share each computers will get? What will be the share? What should be the share that each computer should get? Fair share of bandwidth, right? You don't want one computer to be taking entire 90% of the bandwidth and the rest using the lesser bandwidth. So first things first is, every computer should get equal share of bandwidth. Then when there are 10 laptops in the system, each laptop should get 1 megabits per second. Right? When there are 5 laptops, each laptop should get 2 megabits per second. How is that is ensured? That's the most important thing that you see, which is uh, which is a side product that you get in the underlying MAC protocol. Okay, so medium access control protocol, you might have heard of it. What is the Wi-Fi's? What is the MAC protocol used in Wi-Fi? 802.11. What is the MAC protocol? What is the name of that mechanism? Carrier pin. It's not complete. CSMA bar. Just think one more time. CSMA. There are two types of uh, variants. CSMA CA, collision avoidance. In Ethernet, the MAC protocol that is used is CSMA or CD. Okay. So what is a career sense multiple access? First thing is, why you need that. You understand that this is a MAC protocol used, but why you need that? Because in a broadcast medium, when I am transmitting, nobody else should transmit, right? So it is something like in a kind of in a classroom. Assume that I am the access point, you are all the laptops. Okay, if you want to ask me a question, only you should ask question. Rest of your classmates should remain silent. If multiple people ask questions simultaneously, I cannot interpret your question because it will be convoluted. Okay, it is a collision. Okay, but in a classroom it is easier. Why? Because when you want to ask a question, you just look around, see that everybody is silent, you ask me a question. But in a wireless setting, it is not so easy. Why? It is like a blindfolded. Imagine that you in the classroom, all of you are blindfolded. If you want to ask me a question, what do? You cannot see whether anybody else is asking or not, or engaging with me with the discussion. What you see is, you just sense the environment. If the environment is silent, then you start asking me a question. But even there, two people who want to ask a question, can there is a chance that both of you will be sensing the environment. There is a chance that both of you can simultaneously ask me a question that leads to a collision. So What is a carrier sense multiple access? It works in the same way. You sense your carrier, that is, carrier is the channel. The channel is busy or not, you sense it, you hear. If the channel is idle, there is no transmission that is happening, then you start transmitting, but that transmission may also end in a collision. Why? Because two people who can simultaneously sense and do the same. How do you break this tie? What is the fundamental logic in breaking a tie? Okay, let me step back and ask you another question. If there is only one computer in this access points coverage range, right, you can ask question anytime. When there are two computers, what is the probability of two computers simultaneously transmitting? Which will be relatively less. When there are 100 computers, the chance of two computers simultaneously transmitting two or more will be very high. So more the computers, the probability of collision is high. Lesser the computer, the probability of collision is less. So what is the fundamental information every computer should know within the access point? If somebody tells me in your Wi-Fi range there are 10 other laptops, then you can kind of back off in transmission according to the number of devices. But that's not the way it works, because your computer should not know how many other devices are there, need not know. Okay, so why how things are working in CSMA protocol? CSMA protocol works something like a magic. That is, if every device has the same protocol, the rule is very simple. You sense the channel, that's called CS, carrier sense, and the channel is having a multiple access, multiple devices can access, so it's called as CSMA, right? And the simple protocol in Wi-Fi is that you sense the channel. If it is idle, you do the transmission. Likewise, everybody will do it. Sometime you will see that you will be colliding with the other's transmission. When there is a collision, what you do? You wait. That's the most key point. Wait for how much time? What is that particular time? That's the key engineering principle here. Random time. So random is the very interesting component in terms of security and also in terms of breaking a tie. Let's say I put a protocol in you. You sense the channel. Then if there is a collision, you wait for 5 seconds. You sense the channel again. You will be keying this protocol in every laptop, right? Let's say one laptop is attempting to transmit. Other laptop also has a data to transmit. By chance, both are transmitting at the same time. Now both will back off for 5 minutes. Then again they will transmit again. They again meet a collision. It will be a chain effect. So how do you break a tie? You introduce a randomness. Randomness is you transmit. When there is a collision, you back off for a random time, and then again you transmit. And this is not the only engineering principle here. The random back off is a varying parameter. First collision, you wait for a random time, which will be, let's say, you wait on an average of X seconds. When you again meet a collision, the next time you back off, you wait on an average of 2x seconds, or exponentially you increase your random back off time. That's called as exponential back off. Why? Because you don't know how many players are there in your broadcast domain or a collision domain. So every collision, you increase your back off, which is kind of you're dynamically adjusting your back off, so that you are sensing that, okay, when I'm having more collisions, there are more devices, so I need to wait for more. Then the most interesting aspect of this is this logic of this has a mathematical meaning behind it. Every protocol works in a distributed manner in this way, and finally everyone will settle down with one collision probability, which is a function of number of nodes. What it means is, when everybody is transmitting for a longer time, end of the day everybody will sense their random back off thing. They play like this. When there is a collision, they will back off. When there are more collisions, they back off for more. In this way, everybody is dynamically adjusting their participation. Okay, and this enables every computer to participate and transmit data to the access point. Without this protocol, you cannot have multiple computers talk to an access point in a shared medium, and that is why you need some protocols in the link layer. This is one of the roles played by the link layer, which is the MAC protocol, which will resolve the collisions of devices talking to each other in a shared medium. Okay, and if you study the analytical model behind this, you will see that every device have an equal share of bandwidth. If the total bandwidth that is usable is 10 megabits per second, every computer works in this manner. Everybody will have an equal share of bandwidth in the system. Okay, so we are not going into the mathematics of it, but that is how your link layer protocol works. Any questions? Okay, what is CA and what is CD? We did not get into that. Right, that is expansion. What's the difference? So collision avoidance is when I am transmitting. Okay, uh, so collision avoidance, you can think of something less sensing the channel as hearing and transmitting packet as you are speaking. Collision avoidance is used in a setup where a device cannot do both things simultaneously. As a human beings, we can simultaneously speak and listen, but the devices that requires more hardware complexity and the cost of the radio increases. So that is mostly used in the wired devices where you can simultaneously hear and simultaneously transmit. Okay, collision detection is when I am transmitting, when I am speaking, somebody is asking a question, there is a collision. Right? For example, I speak, I transmit a packet. When the transmit is happening and somebody else is transmitting, his signal will also collide. For example, you speak, your sound wave comes to me, and when one of your friend asks me a question, the sound wave of your friend will reach your ear. By the time it reaches your ear, you stop talking. Right? This is called as collision detection, because as you speak, you can also simultaneously sense your carrier. But in collision avoidance, when you start speaking, you won't hear, which means if you want to ask me a very big question, right? So you sense the channel is idle. Okay, you start speaking, your sound wave reaches me. Before your sound wave reaches your friend will also sense the channel is idle because there is a propagation delay. Your friend will start asking a question, and then both will be speaking, and I cannot able to decode the whole packet. But in collision avoidance, what happens is you start speaking, you sense the channel as idle, you start transmitting, but you cannot stop in the middle because you cannot hear as you transmit. You cannot speak, you cannot hear as you speak, and that is CSMA CA. In wireless, you don't have that hardware complexity, and your chip has to be very. It should perform a low complex job, and it should be cheaper. It should have a very less power consumption. Therefore, the due to the nature of the hardware constraints, the complexity of the transceiver, it does CSMA CA. But in wired devices, you can do something better, which is on a wired device, because the underlying computer can spend more power, or it can have more energy consumption and heat management system, right? So that's the difference. In a collision detection, as you speak, as you transmit, when there is a simultaneous transmission, you can immediately stop because you save some bandwidth. But on the other hand, in CSMA/CA, as you sense the channel and transmit, when somebody else transmit, you won't realize it until you complete your transmission. That is a waste of bandwidth. Okay, so you have to do a trade-off in this setting, and that's why you use multiple protocols in different technologies. Okay, any other questions? The link layer. Now, what are the security vulnerabilities that can happen here? I will come to that once we kind of go through the entire OSI layer. And the other important aspect from a security dimension is what is the key addressing information used in the layer 2? If I want to communicate with another computer which is in the link layer, what is the what is the addressing information I use? MAC address, right? So So the underlying assumption is every computer has a MAC address which is unique to that, and it is a 48-bit MAC address, and 48-bit is divided into two halves, and first half will be what and the second half will be what? First half will be a unique address that is given by the OEM who manufactures that in network interface card. OEM stands for original equipment manufacturer. If a Broadcom is a company that manufactures your network interface card, they will have a unique OEM address, and the remaining half of your MAC address will be a unique address that identifies that network interface. Because the company manufactures many network interface cards, each interface card should be identified in a unique manner. So there is a hierarchy in your MAC address scheme. Now comes the second question, because I'm going into the attack surface of it. What is you are connected to you have a laptop, okay? Your laptop runs an operating system, and then you want to send a chat message to your friend in your lab, and then there are three computers in the lab. Your friend is sitting here, right? So you want to send a chat message to your friend sitting in the computer too, okay? And everything happens in a switch. I'm replacing this with a switch, okay? Or let me use a simple concept. So this is a layer 2 switch, and this is host 1, this is host 2, and this is host 3, and you are sitting here, your friend is sitting here. You want to talk to each other in the layer 2. That is, you construct a frame, MAC layer frame, and you need to have any packet in a network has header and payload, right? Payload is a message that you are transmitting, and header contains information that is needed by the network to steer the packet towards the destination. The most important thing in the layer 2 is you need to have a source address and destination address. Okay, what is the source? What is the source address in your layer 2 frame? The MAC address of your network interface card. This is the network interface card. So this is your network interface card. This network interface card is manufactured by some OEM, and it has its own MAC address. So let's say it has a MAC address of A. It's a 48-bit address. Just for understanding, I'm using a symbolic notation. Okay, so you want to construct a frame, send it to your friend who is sitting in host 2. Okay, and this MAC frame contains source MAC address, which your operating system can pull easily because that is inside your computer. But what is that most important thing that you need to communicate with your friend? In this setting, your friend is in this host H3, right? This is host H2, which has a MAC address B, and this network interface card has MAC address C. Okay, what is that you should know in order to communicate your frame to your friend who is sitting in H3? It's very simple. What is that you should know? You should know the MAC address C. How do you know? In a setting, how do you know? Before sitting, you will ask your friend to WhatsApp the MAC address. All right. So how does it work in a network? So a network designer should engineer this as a part of a protocol. Okay. What is that protocol? What is that protocol? Have you heard of this? Have you heard of this protocol? ARP, Address Resolution Protocol. So in a network, everything should be seamless. End user will not have any responsibility to find a MAC address or an IP address. A network designer or the network protocol designer should bring it in terms of some protocols. So how does it work? See, I'm not trying to give all this jargons, but you should need to understand why you need it first place. Okay. Okay. So all of you come from same college or from different college, right? So you know everybody's name. So if you want to know someone's name, what you do? Ask. Ask in what way? First thing is, in this classroom, you know the particular person, you can ask directly. But in here, you don't. Your computer does not know where your friend is sitting. Okay. So what you do? You should first identify that person with some identifier. Okay. For example, let's say this event management is giving you some IDs, 1, 2, 3, 4 until 30, right? So you wanted to know the name of a person with an ID number 29. What you do now is, there is something wrong. You cannot pinpoint a person and ask the name, right? You don't know where 29 is sitting here. Okay, let's say that is the task. I give it to you. You tell me the name of the person with an ID number 29. How do you do that? How do you do that? Sorry? That's it. You broadcast. You just say that, can I know the name of a person with an ID 29? What happens? This packet has to be broadcast. Broadcast in the sense everybody in the classroom should hear. And who will respond? The person with 29 will respond. Hey, I am 29, my name is so and so. Right? Very simple. That's what address resolution protocol does. Okay? Address resolution protocol has this ID information. What is that? What is the ID here? This IP address comes from the layer 3, which is the network layer. Okay? MAC address is resolved later. Okay, when I want to transmit a packet to my friend, I know the IP address of my friend, which is like an ID number. How to get the IP address we will see later, but we are in the layer 2. We are doing a bottom up thing. So I know that IP address of my friend who has an IP address B. So what I will what I will do is, now I want to know the MAC address of the destination. I know the IP address of my friend. So what I will do, I will say who has IP address B. Okay. Then what is the destination? What is the destination address in ARP? If I want to flood my packet, what should be my destination MAC in ARP? What is the broadcast address in MAC? 48-bit binary is your MAC address. Okay. What is FF? F is the hexadecimal. F stands for all ones. When all 48 bits MAC address is 1, it is a broadcast MAC address. It is a special MAC address which is not used by anyone. So I use my broadcast MAC address, which is FF. All 48 bits are 1, which is a broadcast MAC. Whenever any computer that receives the MAC address, which is FF, it will broadcast. Okay. So which means if I send this thing, switch will receive that packet. That packet will be transmitted to all the outgoing ports, which means that packet is flooded to all other hosts in the network. If I have 100 computers, all 100 computers will receive that. And then only this computer has an IP address B, and this computer may have some other IP address, let's say IP address C. So only this computer will respond with its MAC address. Obviously, the source MAC address is put in this packet, so this guy will know whom to deliver. So it will construct a frame. In that frame's payload, it will put its MAC address. Now H1 will know the MAC address. This is how you will know the MAC address, layer 2 address of your recipient and transmit your packet, which is a very important protocol in network. Okay, whenever you don't know something, you shout out, and that is the same principle used in the network. But this talk is not about network, about security. Security doesn't like broadcast. All the attack surface happens only in the broadcast setup, right? Why? If I want to do a secure communication between two computers, okay, A and B should be trusted computers. They need to have a secure communication. You use all your cryptographic techniques. A will have some private key, and then it will encrypt and send the traffic, and B will receive it, use the public key of A, decrypt it, and then consume the data so that the data is not modified. Everything is sent in a confidential manner. So the entire cryptographic system works when two parties have some cryptographic agreement and then share exchange of keys, right? But when it is a broadcast, one this in a security mechanism, the end users are trusted. Only the middle devices are untrusted. So you establish a secure communication. If end device is untrusted, you cannot do that cryptographic setting, right? Typical cryptographic setting. When it comes to this flooding, you don't know who will be replying, right? So this is essential in terms of a network. For the network to work, to transmit a packet, broadcast is an essential. But for a security, an attacker can easily exploit the system. Okay, and what is that attack that is typically exploited in this ARP protocol? Have you heard of ARP poisoning? ARP poisoning attack or ARP spoofing attack? Have you heard of it? This is most practical attack that people can do in a network. An attacker can simply sit and, let's say, in this switch, okay, wired switch doesn't make sense. Let's say it is a wireless access point. Okay, that is not a problem. Let's say I have another attacker who is connected to the switch. The primary objective of the attacker is to respond to the ARP packets. So, for example, when host is flooding the whole switch, asking for who has the IP address B, okay, maybe the attacker can respond saying that I have the IP address B before host 3, or maybe host 3 is down for some reason or not connected, let's say. Now what happens is our so the spoofing will happen something like this. H1 will send an ARP packet asking for IP address B. This attacker will respond saying that I have the IP address B and this is the MAC address. Okay. So in this way, what you have done is you have made believe host 1 saying that your friend is sitting in this machine, right? Then what happens in this protocol? Before H3 responds, this guy is responding, and then H1 thinks that the MAC address of IPB is this computer. So all the communication happens between these two. Okay, your H1 believe that your friend is sitting in this machine, but actually your friend did not receive. Right? So this is called as ARP spoofing. So anybody in the middle of your network can pretend as the target destination, proxy them, and then receive the packets. And you can also, if H3 wants to communicate, this guy will say pretend that I have the IP address B, IP address. So it can pretend with your H3 and it can act like a H1. So basically what I can do is the attacker can pretend to real H1 that it is the H2, and for the H2 it can pretend like a H1. So it is like, what is this kind of attack? Man in the middle attack, where I will be sitting in the middle of H1 and H3. The attacker is logically sitting in the middle, and whatever H1 is transmit, the attacker can transmit back to H3 also, and whatever comes back, it can also listen. So basically, you have gotten into the middle of the communication substrate. You can over eavesdrop anything that can happen. Okay. So do you understand? In a network, a protocol is designed for a functional purpose. But when you take a look from a security perspective, you can even attack by exploiting the same flooding mechanism or the broadcast medium. Okay. So this is a key technique that people use in ARP. How much time we have? We have a break or 10:15? Right. Any questions in the MAC layer? I hope you understand what is a MAC layer. It helps you to transport packets between the link layer or link layer hops within the LAN. Okay. So now let's move on one more step further in the stack. Let's look at the layer 3. Okay. Why do you need a layer 3? What is the protocol that is running in layer 3? Can you name the protocol's name? TCP is a transport layer protocol. What is okay? What is layer 3? Yeah, somebody said. Yeah. IPv4 is the current thing that we are using, and we are moving to IPv6, but we have not completely migrated. Predominant internet is running on this protocol. IP stands for Internet Protocol version 4. Okay, what is the purpose of this protocol? This is the bread and butter for the internet. What is the purpose? Sorry, host to host. Okay, device to device. Okay, yeah, correct. But what is the most? Why can't you use a link layer here? Especially because internet is basically network of networks. You are not interested to communicate between the devices within the network. Your packet should cross multiple networks. Okay, let's say I have a network here, and I have another network, and then I have another network. So let me call it as network A, network B, network C, and there is a host. Your friend is sitting here, H2, and your another person is sitting here, and both these computers are connected not in the same network, on a multiple network. Okay, maybe this is a home, this is an ISP, this is another home, another home network. Your host is connected there. Okay, now my packet has to travel across multiple networks and reach my destination. Okay, so now things get little complex here, because I have a complex fabric of networks, and each network may use a different technology in the link layer. They use their own some will be on fiber, some will be on LAN, some will be a mix of many things. Okay, so we don't go into the lower level stuff because we are using the principle of abstraction. Okay, now we are in the layer 3. Okay, so just for sake of understanding, let me put another network, network D. Okay, and that is also connected to this network. And then there is network E, and there is a host 3 that is sitting here. If host 1 wants to communicate to host 2, it has to send a packet that has to go to some gateway router. Gateway router is a router that connects multiple networks. Okay, and this from here it has to go to another gateway router. Okay, so there is a common symbol notation. You use circle for router, and you use square for switches, layer 2 switches. So there is a okay. So basically, these circles indicate gateway routers. I'm sorry. Okay, you are talking from a BGP perspective. Yeah, you can think of that way. Yeah. Yes. Okay. I'm not bringing in the concept of this what you call it as AS, right? Augmented systems, autonomous systems. So I'm not bringing that because that is an administrative thing. I just want to keep it simple. Okay. So I'm not talking about a BGP. It is a BGP if you want to think that way. Um, so these are the gateway routers or border routers that you can say. So now if I want to route a packet, if I want you are sitting here and your friend is sitting here, okay, and everybody has unique IP address. Okay, so your IP address is A, and your friend's IP address is B. And I want to ask another fundamental question here. In a computer, IP address is assigned to a computer, or IP address is assigned to a network interface. What is the answer? What is your answer? Yeah, please be louder. Network interface. So there is one common misnotion that every computer has one unique IP address. It is wrong. Every computer has multiple network interfaces, and each network interface will have its own IP address. For example, your mobile phone is a computer. You are connected to Wi-Fi, you will get an IP address from your Wi-Fi NIC card. If you are connected to your cellular data plan, your cellular network card will have a different IP address. So each network interface card will have its own MAC address and IP address. Okay. So now, what is the first thing that you should know in order to send your packet to your destination, your friend? Let's say it's not a friend, rather it is your some website. Okay, this is a machine that runs a website. Let's say this is google.com. It is a web server. Okay, if you want to access google.com, you need to know the IP address of the google.com. Obviously, you did not care about knowing the IP address. You open up your browser and type google.com. Is that correct? First thing, if you want to connect to a Google server is not sitting in your network. It is sitting somewhere in a different country, and you are connected to Google server over multiple networks along the way. First thing that you want to send a packet to a Google server, what you should know? The IP address of the Google server. How do you know? Sorry? How do you know the IP address of Google? Yeah, please be louder. DNS, right? So you have heard of the service called DNS, domain name system. Okay, domain name, it is a service and a system. Okay, so this is something, if you want to think in a very simple term, you can think of yellow pages. What is yellow pages? I know the name of a person, but I don't know the phone number of that person. I open up my phone directory, which is in olden days it's called as yellow pages. Hope you have heard of this term. You open the yellow pages and then you look into the name, in some alphabetical order, and then you find the particular person's phone number. DNS is the yellow page of internet. Okay, somebody says google.com, you remember google.com. That is the human readable name which you all can remember. Netflix.com, Amazon.com, right? Um, so DNS is basically a lookup service. It is a system. It has a system. It is a distributed database. End of the day, it maintains all the list of domain names and their IP addresses. Okay, it is an application layer protocol. Okay, so how do you know the destination? The Google.com's IP address, which is B. I use an application layer protocol, which is DNS. In a DNS, you first send you want the IP address of google.com. You query the DNS with your domain name. It will give you back your IP address. Okay, so that is the application layer service that you first need to know the destination's IP address. Okay, in Mac layer you don't need to do that because it is a very small set of devices. You can flood it and then get it back, but you cannot flood a big network just to know the IP address of Google. Likewise, if everybody does, then most of the people will be flooding the network only with these queries rather than transmitting the original packets, right? So you have a different setup in the when your network is very complex. This is only first piece of puzzle solved. What is the next one? Using the DNS service, you know the destination machine's IP address. And what is the other piece of puzzle? Where is this IP address located? You ask DNS, DNS tells you the IP address is here. But what is the most important aspect of the network layer? This IP address could be here. This IP address could be in some other device here. How do you know? How do I know where this IP address is sitting? Right? You don't know. So that is where IP layer comes in. IP layer helps routers to learn how to route packets to different destinations. Okay, so all these gateway routers that are sitting, which runs IPv4 protocol, one of the key functionality of that protocol is the routing algorithm. They try to talk, they try to advertise. For example, Google is sitting here. This is a network that is directly connected to the Google. Okay, what this network will do is, this is where the BGP comes. So what this router will do is, it will tell to every other gateway, hey, I have a google.com sitting with me, and if you want to reach google.com, you can route your packets to me, and this information is shared to the nearby routers. Likewise, every routers will share the information. They learn the routing information of reaching different people in different networks, and that is where IP protocol comes in, that learns route how to route packets to different computers in the system. Okay, this is the second piece of puzzle. There is another piece of puzzle that your layer 3 has to solve. What is that? I know the destination IP address. My IPv4 protocol, which is running in every router, will learn how to route to different hosts, destination hosts in the machine. And what is the other thing that I need? Sorry, that is where the router thing, which network you need to forward so that finally it will be delivered. That is done. But if you want to construct a packet, what are the three things? Payload, obviously you have some content to transfer. Destination IP, what is that? Source IP. Who assigns source IP? Who assigns IPA to your machine? For example, you are new to this institute. You brought a new laptop. You are connected to your institute's Wi-Fi. Who assigns IP address to you? Network administrator. So you will go to the administrator, get an IP address. You don't do it, right? So you don't go to the administrator, ask for an IP address. You assign me next unique IP address. I will use it for my internet. It doesn't. It happens so seamlessly. You just go connect to the access point, and then you are authenticated. You get an IP address. You get connected. Okay, it is assigned by a system inside your network. What is that? What is that? That's also a protocol. Which protocol assigns you an IP address when you are connected to the system? RARP is a reverse ARP. Whatever you do in ARP, you're doing the reverse of it. Have you heard of this? We heard of this protocol DHCP, right? So dynamic host configuration protocol. Okay. So typically the enterprise network, they run an application layer on a server, which is a DHCP server. Okay. So this DHCP server's job is to listen for DHCP packets, and anybody who joins the system who does not have an IP address of their own, what they do is your operating system will run a DHCP client. You will have a DHCP client that is running in the system, and this DHCP client will send a packet. And in order to reach a DHCP server, you should know the IP address of DHCP, right? That you don't know. Okay? So what you do, it's the same logic. When you don't know anything, you shout out, right? You send a broadcast packet that can run in your network, and finally the broadcast packet will reach a DHCP server, and the DHCP server says that, okay, there is some guy who is sitting in my subnet who needs an IP address. It will assign the next available IP address to that particular computer, and it gives a lease time so that the IP address remains assigned to that particular host for some time. Why should I lease it? Why should I not permanently assign a number? Because IP address is 32-bit. I can have 2 port 32 combinations, not precisely. Some numbers, some addresses are reserved. I have only a finite number of IP addresses. I cannot permanently assign. So I can lease it out. After some point, the device leaves my system. I can assign the same address to somebody else. So IP address is a kind of a very critical finite resource that I need to manage. Now, what is the attack surface here again? Again, attack surface is you are broadcasting your packet because you don't know where the DHCP server is. You broadcast a packet asking if there is a DHCP server, please assign me an IP address. If it is a trusted DHCP server, that is fine. You get an IP address because that DHCP server is configured by the network administrator. You get an IP address, use it for transmission. Let's say there is an attacker who is pretending like a DHCP server. An attacker can give some other IP address to you. Okay, so what will happen? You will not be connected to the internet because your enterprise could have blocked you, can block any other IP addresses that are going out because it can cater to only the subnet of IP addresses that it is using it to serve the clients. So it is some way of blocking you out of the internet, right? So this is called as DHCP side spoofing. I can pretend like a DHCP server, and I can kind of absorb all the clients into my system. And this DHCP service is a most critical part because when you're getting the IP address of that is getting assigned to you, you will also get all critical information about the network connectivity. Can you tell me one critical information? How do you know the IP address given a domain name? I want to know the IP address of google.com. What should I do? What is the application layer protocol that helps me to resolve it? We just said. DNS. So DNS is an application, right? So DNS is a server. There should be some server that should be running this thing, and you should ask that query that server and get the IP address. How do you know the IP address of DNS? That is being provided by this DHCP server. So DHCP server not just gives you an IP address, it will also tell you the DNS server that you want to look for. The IP address of the DNS server will be provided, and the gateway router. This gateway router has an IP address, right? So this gateway router IP IP address, all this necessary information is provided by the DHCP. So once you connect to a network, that network will give you all the information. You want to look up for the domain name, you talk to the DHCP server in this IP address. If you want to route your packet, you route your packet because the gateway router in this network is here. You route to the gateway router in this IP address. All the information is provided by this DHCP server. When an attacker pretends like a DHCP server, what can happen? What can possibly happen? An attacker can send IP address of google.com. The real IP address of google.com could be something else. An attacker can run its own local DNS server. While assigning the IP address, it can also say that for DNS also you look up to me. You send your DNS query to me, I will resolve it. So what you do is in your browser you type google.com, and the google.com's IP address will not be real google.com. Rather, an attacker would have created a kind of a pretending web page that looks like google.com, and the DNS service is also in the attacker. So you send your DNS query to the attacker, not to the real authentic DNS server. This guy will reply back with an IP address which will be running kind of pretending google.com Google service. So you do whatever you do, you can even send in your Gmail address and things like that, right? Your password gets compromised. So DHCP attack is very serious attack here. You know, you get the difference, because in a network, for network to work seamlessly, broadcasting is a very fundamental protocol. But from a security perspective, an attacker can easily exploit it. So if you want to understand one single notion in a network security, broadcast is a necessary evil. It is necessary, but it is evil. You need to protect against it. Okay. So DHCP server, if that is compromised, if somebody pretends like a DHCP server, he can completely kind of take you out of the system, and whatever you want, the guy can kind of channel all the information through the guy, and they can eavesdrop or even control, take out all your passwords and things like that. Okay. For example, if I run a website like an Amazon, that looks like a ditto like a original Amazon.com website, but you don't know the real Amazon's IP address. If DNS server is also compromised, I will give you a local IP address where I run my own dark Amazon.com. Then you will be directed there, right? So everything will be compromised because the yellow pages are compromised. The gateway router I can compromise. I can also spoof you with different IP address. You think that you are connected to the internet, but you are connected to the attacker's network, right? So that is another serious issue in the layer 3. Do you get the attack surface? Over the time, we'll see how to mitigate all these things. But I'm just introducing you the functionality of the network and then the attack surfaces that are most potentially can be exploited by an attacker. Right? Any questions in layer 3? Okay. Fine. Internet is network of networks. I have a protocol that helps me to connect computers from one network and to another computer connected across multiple networks. The job is solved, right? Why do you need higher layers? Because that's where we are going at it. Why do you need layer 4? Before asking why, what is the protocol used in layer 4? Okay, so UDP and TCP, predominantly internet uses UDP or TCP. Why? Yeah. Okay, I will come to that. So what is connection oriented and what is connectionless? Okay, I will come to that again. And okay, now you understand the transport layer uses TCP, which is a predominant protocol used in internet. Almost 99% and above devices use TCP because it is connection oriented and most importantly, it is reliable. Okay, you know why a TCP protocol was invented in the first place? Why TCP is required? Not for reliability or connection oriented. When the internet was invented in the very first time, It was used in very restricted places in the academia within the universities for research. Later, internet was commercialized when big people came into place, and internet is used by almost everyone in the globe. Okay, at that time there is no notion of transport or TCP protocol. Okay, but what happened is when soon the internet was released as a commercial service, everybody want to connect to everybody else over the globe. What happened is at one day the entire internet was blacked out, which means the entire internet was broken. Nobody could send traffic from anybody else. The fabric is there, network of network is there, IP protocol is there. You know how to route the packet. You can send the packet. The packet can be routed among the across the routers. Finally, is delivered to the destination. But what was very surprising to them was, as everybody was connected, nobody could able to send the traffic. You know what was the issue? What could be the issue? What could be the issue? The logic wise is correct. I can know how to I get the IP address of the destination. There are no attackers in the system. Everything is fine. But internet was completely blacked out. Nobody could able to connect with anyone. No single packet could be delivered. The reason is everyone was greedy. That is, imagine that every computer has a bucket, right? And the entire network has like kind of pipes connecting to all these buckets. You want to transfer, you pour water. You want to receive, you get the fluid, right? So what happens is everyone started pouring data inside it. So it is like something like you have a road network. You kind of bombard the whole network with a lot of cars in it, with no traffic regulations or control. So what happens? Traffic jam. Every packet will get stuck in every router, and router is also a computer, and computer has a finite RAM and storage, so it cannot store all the packets. Beyond some time, the RAM gets filled up. Every other packet that comes get dropped off. So what happened is nobody has a regulation of the traffic. Okay, everybody started. Okay, I am connecting to some other friend. Let me push the packet to the friend because there is no charge in transmitting your packet, right? So everybody started putting the traffic. They kind of choked the whole internet and got collapsed. And that is when the network engineers and researchers went back to the table. They were thinking what was wrong in the whole system. The whole system is the people don't recognize that this bandwidth is limited. Everyone can send the traffic in a more cautious manner, and that led to the invention of this protocol, which is TCP. TCP is one of the finest protocol, which was invented with some logic, and there are several variants of TCP, but the core logic of TCP still remains the same. And to everyone's surprise, you see that many technologies are superseded or replaced by some other technology, but TCP is a protocol that is still surviving ever its inception. Okay, that's most important thing, because a TCP provides, other than reliability and connection oriented, it provides control mechanism. What are the two control mechanism? These are the two important mechanisms that TCP provides, which is a flow control and congestion control. What's the difference? What is a congestion control? Fine. What is a congestion? So when the network is congested, what you should do? You should stop. You should stop sending the traffic, or you should reduce the sending rate of your traffic. If the network is not congested, you will send more traffic. Okay. So now TCP gives you a kind of a regulation. It is like a tap inside your. You are connecting a tap to the pipe. Earlier in the IP network, you had a pipe. You have a pipe. The water will freely flow. Now you are introducing a tap where you can control it. That's what TCP is doing. What TCP does is, if it senses the network is very congested, it will control its rate. That is, you reduce the diameter of the pipe so that you cannot push more traffic. Okay, so eventually when everybody does, what happens? The the traffic jam clears out, because when everybody realizes there is a congestion in the network, everyone controls that sending rate, then the amount of traffic that goes into the network per unit time reduces. Then the routers try to breathe out, the packets will be delivered. Then when the congestion is free, everyone can unloosen the tap, they can send more traffic. So do you see, I can do a dynamic control here. When there is a congestion, I tighten my traffic. When there is no congestion, I release my traffic. So this is automatically done without user intervention by the operating system which implements this TCP protocol. That is congestion control. What is flow control? What is flow control? Some precise way of saying what is a flow control. So imagine network is very good. Network is not congested. What could go wrong? The end device has no capacity to digest the information. That is, network is good. I have a very high speed network. I push a lot of traffic, but finally this traffic goes to the destination machine. In the destination, this traffic will be stored in a uh, some RAM space is reserved, some buffer is reserved. The packet gets accumulated there, and finally this packet is consumed. Let's say you are watching a movie, and your playback rate is very small, and the buffer reserved in your storage receiving device is very small. My network is good, I can push all the traffic, there is no congestion, but my buffer is very small. What can happen is your buffer can get easily filled up, and what will happen after that? The buffer will overflow. Even if the network delivers the complete packet, the packet is not useful because your receiver has no enough buffer to store it for consumption. It is something you are feeding food to baby, and you can deliver the food fast to the baby, but baby has some speed of consuming the food. You cannot kind of just put all the food, eventually it will spit it out, right? So this is flow control. Flow control is, it is not due to the congestion in the network. The receiver has some buffer capacity, it cannot consume more. So when the receiver's buffer size is kind of getting shorter and shorter, smaller and smaller, it will send an advertisement packet to the sender. Hey, don't send me more traffic because I don't have enough place to store. So sender will again control the traffic, not because of the congestion in the network, because the buffer capacity is very small. And this is flow control. Okay. So TCP does two important things. You have a network. When it is congested, you react to it by reducing. When it is not congested, you increase your traffic speed. The other hand, flow controllers, the buffer capacity is more, you send more traffic. Buffer capacity is less, you send less traffic. End of the day, your TCP does the min of these two. If congestion is there, it will control. Buffer is not there, it will control the traffic. If congestion is good and congestion is not there and buffer is capacity is high, it will release more traffic. It is a min of these two functions. Okay, so you understand why a transport layer is required on top of IP layer. IP layer tells your host source where to send the packet, how to send the packet, but this one controls your traffic. Okay, that's why internet predominantly runs on TCP/IP. TCP is a layer 4 protocol and IP is a layer 3 protocol. Okay. Now, so this is the functional requirement of TCP. On top of that, these are the other benefits that TCP provides. Okay, and these things are possible only because your TCP is using a connection oriented paradigm. What do you mean by that? Sorry, that is the mechanism for establishing a connection. There is a three-way handshake. You establish a connection, then you do the data transfer. Finally, you close your connection. That's the mechanics. The question is, what is connection oriented? Why do you do a connection establishment? That's the question. In order for ensuring the reliability, when you do the transmission, the packet is dropped or corrupted, you need to retransmit. So there is a connection between first packet and second packet because you may be retransmitting, right? When you are controlling the traffic, you are controlling the traffic between one application here and another application here. So there is a sequence of data that is transmitted which is related because you are not sending multiple traffic in the TCP. A TCP is a is between what pair of entities? TCP provides a connection between two pair of entities. What is that? Host to host, process to process, application to application, right? So basically, let's say you are watching a Netflix movie. The TCP connection is between your nearest CDN server, Netflix ASC server, which sends a stream of movie packets, and your video player is you are watching the video on the other end. So TCP is a process-to-process communication. All the packets that are sent in that pipe has some relation. They belong to the same application or the process. So there is a dependency between one packet and another packet. If one packet is lost, you need to retransmit the packet. There is a way of identifying it. And if the packet is received in an out of order, you need to rearrange it. For that, you need this notion of connection orientedness. You need to have a pipe because your IP, your network is not connection oriented. Your internet is not connection oriented. What do you mean by that? Your internet is driven by switches which are running, which are packet switching devices. What do you mean by packet switching? Every packet has its own destination IP and source IP, and each router has its own rights to route the packet in different manner. For example, let's say your entire Netflix has two packets. You want to watch a very small video where your entire video packet is two TCP packet. In a process to process, you logically say that these two packets belong to these two processes. But when it goes to the network, one packet can take a different route to reach that server, that process. Another packet can reach a different route because your network, internet is a packet switching, is run by packet switching devices. It will switch each packet to different, it can steer each packet to different routers as well. That is also possible. So connection orientedness is required because you need to connect all these packets and then order them. One packet will come in a very fast path. Another packet can come in a slower path. Maybe the first packet comes later, second packet comes faster. You cannot watch a movie in reverse, right? So you need to order the packet and then give it to your application. So for all these things, connection orientedness is required. Connection orientedness is nothing but whatever order I am sending the packets in the sender process, the receiving process should receive the same set of packets in the same order. Everything should be uncorrupted, okay? Nothing should be tampered, and everything should be received in the same order the sender does, but the underlying network kind of mixes it up, okay? So that is the connection oriented nature. That is where you need to establish a connection between the sending process and receiving process before transmitting. Then you transfer a sequence of packets that is delivered. The transit can be random order, but at the receiving end, everything will be arranged in order and then sent to your application. So application thinks that the network is very good and everything is sent in a sequential order. Sorry? Yeah, I will come to that. So that is the functionality of the transport layer, and this is where the attack surface happens. Okay, so maybe we'll discuss after the break. So we have come to the transport layer, then we'll do the application layer. Then the second part of the talk will be, we'll be assuming that all this layer familiarity is there with the entire audience. We'll just glance over the design and see the different attack surfaces. We'll revisit and see what are the countermeasures, mechanisms, and some techniques that we can adapt in the design of our infrastructure. Okay.